So in this discussion, I'd like to talk about what is a basic FIR filter block and then one that one builds upon in many different places, which is basically doing a differencing sort of filter. Now, this very basic thing has two coefficients, a +1 and a -1, and x of n and x of n minus 1. You'll see this all over the place in many, many different approaches, and you'll see sort of additional aspects of this all over the place. And where this really comes, this concept comes from, is saying I want to make an approximation. It's actually usually meant to be sort of a high-pass filter kind of starting point. But the real perspective is, well, what would happen if I had a derivative? Y of t equals dy, dx of t dt that you may remember from somewhere. And what's interesting is that will be x of t minus some delta, t of delta behind that, over that sample. Well, if I'm looking at a sampling and delta is the distance between my two samples, which is as small as I can get if I'm trying to do a derivative approximation on a sampled system, well, okay then, that's probably going to be 1, that's going to be just 1, and so I get sort of x of n minus x of n minus 1. So this is the kind of difference I get. Maybe another way to ask this question is, what would my system look like if I tried to take a derivative based on samples or an approximate derivative? This is another way to ask what's happening here. You would imagine that from this, my impulse response, if I put an impulse into this system, I'm going to get a 1 and a minus 1. Okay, so fair enough, right? So this is now the kinds of functions that I would expect to see in terms of my impulse response, in terms of my function. So what does this do practically in a real system? Well, I would love to see having a derivative. Well, let's pick a signal, again, that has many different signals in it, so it's constant. It's got a big jump here. It looks like a step and drop, but it looks like I've got this other thing happening on top of it. Well, what am I going to see in terms of its impulse response? Well, again, everything will start at 0 because nothing starts until 0. Even this doesn't start till 0. And what do I see? Well, I see an initially jump of 1 up initially. So I see this rising edge get brought through, and the size of it is 1, which is no surprise given what the impulse response is. But then interestingly enough, it looks like it's pretty much nothing there until I get to the end, and then it drops, and it has a minus 1, which is basically giving me an indication that there's a minus dropping edge. Ah, right, well, there is a major change there. I would expect to see that. All right, so if that's what I'm getting, well, what else should I expect then as I look at this? Well, if I look at stuff that's varying in the middle here, there's a little bit of variability, and notice that the variability comes through. But the sort of rough constant term disappeared. This is probably what you would expect for a derivative, but also interesting to see what you get here. Now, fascinating enough is I can actually now ask, what is the frequency response? Well, again, I can take a look at this difference equation and pull it across to over here. If I know something about z transforms, I know that this is then, there's going to be a z minus 1, and that z minus 1 converts to an e to the j omega in the frequency response, and so therefore I get e to the j omega. And you're like, great. Now, how do I approach the rest of this? Well, that turns out to give me this term. I'm going to pull out e to the minus j omega hat over 2 out, because that'll then give me effectively my phase term. And then I get a plus and minus omega over 2, so that gives me sort of a sine of omega over 2 term. Interesting, right? It definitely will change sign. I definitely need a j in front. So clearly, there is a sense of getting a 90 degrees shift potentially, at least if I'm using a sine kind of approach here. And what's interesting then is if I actually take this structure and actually compute its phase, a couple things happen. The first thing I notice is if I compute h of 0, well, that's going to be 1 minus effectively 0, which then gives me 0. So I know I'm sitting at 0 with 0 phase. I also know if I'm sitting here at omega equal to pi, well, this is then going to be minus 1. So minus 1 is 2. And then it's going to shift in between. And so that's just something to kind of notice and how and what's going to happen in terms of the phase and some of the behavior. There's a clear jump in the middle here in its phasing because I'm going through 0. So every time I go through 0, I get this sort of negative term in there. So again, just things to kind of be watching for as you look at this. But notice what I get. At high frequencies, I get things that pass through. At low frequencies, I get basically everything at 0. And then, so there's almost nothing here. In fact, it's a 0 at 0, which means that basically right at 0, I get nothing going through. And then it continues up as I go out. So it's a very interesting function. You can definitely see that you can see the high pass behavior. This is what the approximation of a derivative looks like. You can definitely see the j term sort of show up in the sort of plus and minus pi sort of the half of pi in there. Again, also very relevant as you look at the behavior. And so this just gives you an interesting perspective of how to interpret what you see when you're thinking you're taking a numerical approximation of a derivative.